from last week's hashing lecture, and then I will go through my lecture and I'll give y'all a problem set at the end to work on for the next week or however long the next meeting. So first of all, let's go to Victor, who will be explaining the solution to a problem.
Okay, so let me share my screen. So basically, in case you guys were not there for 2 weeks ago's meeting, you can find the PowerPoint that I used for the lecture in our public drive. It's just like bit.ly.cs club drive, and then you'll find like if you go to the meeting, there's the PowerPoint and the solution to the problem I did in that meeting. But today I'll be going over one of the problems from the set of practice problems that I gave you guys last time. So it's going to be this problem from a USICO 2017 contest. And basically, for this problem, okay, if you guys haven't read the problem, I'll explain it. So this problem statement is kind of like, it's kind of confusing. Like I didn't completely understand it the first time I read it, but basically you're given these list of genome sequences. So there are n spotty cows and n plain cows, and each genome sequence is n characters long. Okay, so Farmer John wants to find the length of the shortest like range of indices that can be used to explain spottiness. So what that means is like he wants to be able to choose some consecutive range of indices, and it has to be such that it's not like a spotty cow and a plain cow cannot have the same sequence of letters over that range of indices. For example, if he wanted to choose this range of indices, like indices 3 through 6 to explain it, that would not work because oh yeah, by the way, like the way the input's formatted is like the first n cows are spotty and then the last n cows are the plain ones. So here, this first spotty cow has TCCC over these indices, and then this plain cow has TCCC over these indices. So if he saw a cow that has TCCC in these indices, then he would not know whether it's spotty or plain. So like we would say that this sequence of indices, this range of indices, could not explain spottiness versus plainness. But on the other hand, the example they give is 2 to 5. If he chose these 4 indices, then this range of indices could explain spottiness, because you'll see that like these sets are completely disjoint. Like if you put ATCC, CTTG, and GTCG in one set, and then you put these 3 strings in another set, they would be disjoint sets, which means that they would have like no elements in common. So that range of indices would explain spottiness. So he wants to basically find the shortest sequence, like the length of the shortest range of indices, so that can explain spottiness. So basically a few observations that we have to make for this problem. So the first is that we're asked to find like the length of the shortest sequence. So one is that we only need to find the length itself. Like, I mean, we only need to find the length of the sequence, not the shortest sequence itself. I think for the solution that I have, that actually it doesn't matter, but that could be something that you want to note. But also is that if you take a sequence that works, for example, like ATCC, or like this indices 2 to 5, or yeah, 2 to 5, and you increase the length of that sequence. So like you add on like index 6, so now you use indices 2 to 6, then like that could only help you. Like that would only give you more information, which would help you explain spottiness, right? Because if 2 to 5 already explained it, then 2 to 6 will for sure explain it, because you only gained more information. Of course, like you wouldn't want to use 2 to 6 if 2 to 5 already works, because you want a shorter one. But it's just where using like building off of a shorter sequence and making it longer can only make it more likely to explain spottiness. So from there, we can realize that there's some threshold, right? Like all the, okay, let me start drawing in Sketchpad. So like all the values, like starting from like in the beginning, the very short lengths cannot explain spottiness, right? So basically, we're basically going to denote if a length. Okay, I'm first going to write out the lengths that we're trying to consider. So like these numbers represent like the answers. So like, can we find a sequence of length 1 that can explain spottiness? And then I'm going to make the value 0 if it cannot, and make it 1 if it can. So we know that like at the in the beginning, like a prefix of them are all zeros until a certain point it becomes a 1, right? In this case, the shortest one is length 4. So like so 4 would be the first one, and then after that we know that like it's definitely all possible up until like the length of the whole string itself, which is 8. So basically I mentioned in like my binary search lecture a few weeks ago that if you see the problem have this property where there's some minimum threshold where everything to the left of it does not work, and then everything to the right of it does work, then like that motivates binary search. That wasn't actually a complete explanation. I could have gone more into depth with it because not every problem that has this property is actually binary searchable. Like for example, if a problem is like a BFS problem where like it just asks you, given some graph, what is the shortest distance between 2 points? So sure that it does seem like that is it seems like it's binary searchable because it seems like it matches this property, where below this certain shortest distance it's not possible, then above the shortest distance it is possible. While it's true, like another property for a problem to have to satisfy to be binary searchable is where you can quickly tell if one answer is correct, right? So in the BFS example, you can't really like easily tell if 2 nodes are 6 distance apart, right? Like it's pretty much just the same problem itself that you're asked originally. So if you have a problem like that, then like that's not really binary searchable. So here, once we see this property, it's not immediately binary searchable, but like we can kind of like pursue this train of thought and see if we can quickly tell if like a given length is possible. So like let's just like try to pursue this train of thought, and let's say we're just trying to test if a certain length is possible. So like we're trying to tell if length 4 is possible. What we can do is just is like perform the process that I briefly described. Basically, you would construct a set where so you would, if you're trying to see if length 4 is possible, you would go through every substring of length 4. So you would start with this leftmost substring of length 4 and add these first n substrings into a set, and then add these last n substrings into a different set and check that they're disjoint. And then we would continue on. We would check for we would just shift this substring over and then repeat that until we get to the last substring. We just continue all the way through. So if you think about how long that would take, right? So like if you were to just use like substring and stuff, the length of the substring can pretty much be m itself, right? Which is like 500. And then you would have to go through all 2n of the strings. So like that's like 2n is going to be 1000. And then like the number of times you can shift it, right? Because you have to consider every substring of the given length. So then that's another m. So that would pretty much be like 500 cubed at that point, which I'm not sure if that actually runs in time, but I think it probably does not, because 100 million is usually like the threshold where it would run in time. So it may be borderline run in time, but I'm not sure if it can run in time. But let's try to make a solution where like we're more confident that it will run in time. So we can use hashing to basically compute like the hashes of these substrings instead of having to use the substrings themselves. So instead of storing these like substrings in a set, we'll instead store their hashes. So when we do that, like when we shift the hash 1 to the right, that only takes like a O of 1 time change instead of having to like restore the entire substring. So if we use a rolling hash to maintain all the hashes, then the time complexity of like checking whether a given length works is just n, because you have to like do a rolling hash for each of the n strings times the length of the string, because you just have to like you compute the initial hash of the initial substring, and then you shift it along, and in total that would just be m time. So it would take n m time to check whether one length works. So that's just 500 squared, which is only like 250,000, and then times the log m, because we're binary searching on the length of the sequence. I can explain it, and we're guaranteed that nose body cow has the exact same genome as a plain cow. So that's actually pretty key, because that tells us that like the maximum answer is m. Like if we choose m, then we will for sure be able to explain this bodiness. So that like kind of like puts a bound on our answer. So now that we kind of have the solution, let me basically code this problem from scratch. I already had a solution, but let's walk through the solution. So let's call this cowonomics. Okay, so basically, okay, let's just I basically have this template for these kind of problems. So we're basically gonna basically all this does is like I have these like pretty convenient functions like s, which pretty much is the same thing as in.next like in scanner, and I does like in.next int. So you kind of see that like it kind of makes coding this problem a bit easier. So okay, I'm gonna put this on a separate screen so I don't have to keep tabbing between them. So the first thing we have to read in are like the input. Actually, I should probably just keep tabbing between them so that like you can see what I'm talking about. So first two input things are n and m. So we'll just read in the input, and then we have to read in like the n spotty cows and then n plain cows. So we're actually going to store these as char arrays, because in Java you have to use .char add to access like a character in a string. But if you just make it in a char array, then like it's more convenient to access. So we'll call the first one spots. Okay, so the first n are spots, and then like the dimensions are going to be n by m, right? And same for the plane. So we're basically going to just read in the input, and yeah, we can use the s method that like I talked about earlier, just like read in the next string. So the current cow is just like the next string, but then we're going to use the toChar array method, which basically just converts a string into its char array. And then we're going to do the same thing for all the plain cows. Okay, so this reads in the input, and now we're going to set up the binary search. So like we have to like understand what the balance of the binary search will be. So low is like the minimum possible answer. So that would be 1, right? Because you need at least a length of 1 sequence to be able to explain something. You can't really have like 0. And 1 is possible because like if maybe they're all like there's just one, like n is 1, and then like they're each just 1 character long. So then you have A and then G. So then a 1 length sequence would explain it. So 1 is the minimum answer, and then the height is just m, because the highest we need would be m because of like this condition. If we just use the whole genome sequence to explain spottiness. So now we're gonna like put the actual binary search code. So like the condition, like the general condition in any binary search is just low is less than high, because once the two bounds of the binary search are equal, then you pretty much finish your search. Then the two bounds which are equal will be your answer. So so like when you are writing binary search, you would pretty much guess like the middle value, like low plus high over 2. So, and then based on whether like len works, you would be able to update low or high to like something near len. So then that would perform the binary search iteration of having the length of the range that you're searching over. So len is in the body of this loop. Len will be like the length of the sequence that we're trying to see if it works. So we're gonna have some like code to see if len works. Okay, so now let's say that I after we've written the code, we're gonna check whether it works. So we're gonna have a boolean that just called like works. So if it works, right? If the length len can explain spottiness, then that means that okay, let's go back to the sketchpad here. So that means that we found something that works. So say like we're in here, we found out this works. Note that we want, like when this loop terminates, we want to be able to output like low, which will also be high, but yeah, low. So we want it to end on like the position of the smallest one, which is in this case is this. So if we found something that's a 1, then we want to move high to equal len, right? Because that would mean like instead of the bound being here now, the bound would be here, and then that would ensure that like the earliest 1 is still in the range, because it could be the case that we actually found this. So then you want high to point here instead of like 1 to the left of it or something, because if you point a 1 to the left of it, you might delete, like you might limit the range to not include the earliest 1. So we're going to set high to len if it works, but if it does not work, like if we chose this one, then we can set low to len plus 1, because we know that len does not work. So the earliest one that could possibly work is just len plus 1. Right. So this is going to be like the update of our binary search. So now let's actually write the body of this code. Now that we have like the overall structure of the binary search set up. So we're basically going to need to first compute the initial hashes of like all the strings. So okay, so we're going to basically have an array called s hash, which will basically store the hashes of the n spotty cows. Yeah, and then pretty much the same array for the other one, for the plain ones. So what we're basically going to do is, and then we also said we have to store a set where okay, let's use a hash set. So we're going to store all the hashes in these sets. So like s set will basically be a set that stores the hashes of the spotty cows, or like the hashes that I'm talking about are like on the given substring as we loop through. Like s set would basically store like if we're considering this substring, then it would store the hash for this, hash for this, the hash for this. Then when we shift over to consider this substring now, we would clear the set and then add the hash of that string, the hash of this, and hash of this. Right. So then that would allow us to be able to compare whether these two sets are disjoint or not. So we'll call this p set for the hashes of the plain ones. And then we first need to loop over the first len characters, because like that's the initial substring that we have to like build the hash of before we like begin the rolling hash of just shifting one by one. So okay, so here this is where we actually need to introduce our like variables at the top, like which will be like useful for hashing. So the first is the base, which I'll just like arbitrarily set to 29. You can pretty much use almost any number, but and then we'll use mod, which a pretty common one is 1e9 plus 7. And then we're also going to need to have a method for exponentiation, because that will be useful to compute our modular inverse, to be able to perform division. So basically what this method is just computing is like b to the power of e mod. So to compute this fast, we're just gonna like recursively divide up the exponent. So we know our base case needs to be where something where like e is 0, in which case we can return 1, because if the exponent is 0, then the answer is 1. And then otherwise we would just store the square root of the number, like b to the e. So that would basically be expo of b to the e over 2. And then if you have to check whether e is even or odd. So if it's even, then you can just straightforwardly return square root times square root, because the square root of a number times the square root of a number is just the number. And then we of course have to mod by mod, so that the numbers don't become too big, and then otherwise we can just return square root times square root, but then we have to multiply another b because e over 2 would do integer truncation, so then you have to multiply it by this extra b. So we can see that here, like with every call of the function, the exponent would be being divided by 2. So like the runtime of this method is just a log of e. So like, it should run pretty fast. So basically, once we have like that mod stuff set up, we can basically start going through all the strings. So okay, actually I'm gonna change these to j, so that like I will represent which string you're on, and then j will represent like which index you're on. So we're gonna loop through the like cows 1 through n, 0 through n, and then we're basically gonna compute the hashes. But okay, actually I forgot about one more thing. So basically we have to pre-compute the powers because basically like for hashing, right, you have to like it would make the adding of the hash more convenient if you could just like use a lookup table to look up what an exponent was. So it's going to be of length m because like that's the maximum length of a hash you're going to need, because the longest string is of length m. So the base case is just pow of 0 is 1, and then the rest of them will just be based on the previous element. So like pow of I is pow of I minus 1 times base mod, where like, so pow of I will be base to the power of I. So like this is so this will be useful when we shift like the hash, and also when we just construct its hash. So so in the inner code of this loop, we're gonna take the current, like the hash of the current spotty cow, and then just like add to it pow of j times like the current value, which is spots of ij, because like that's the character at the current thing we're considering. And then obviously we have to mod it by our mod so that like the numbers still stay within like less than mod. And we can pretty much, in the same loop, we can do the same thing with the plain cows. We can just we can pretty much just add this. Wait, I just typed this. So yeah, it would just work. The logic would work out the same way. So pretty much at the end of this, what this has done is it's computed like the hashes for all the strings, but just with the first like len length substring. Okay, so now we need to add all these hashes to like their respective sets, right? You have to add all the spotty hashes to the S set. So let's just write like an extra loop here where we add we're like, okay, set dot add. So here we're just adding like the hashes to their respective sets to be able to compare them. So now we're gonna have a Boolean called works, which is like thing we're gonna use here. So it's gonna start out as false, right? Because we don't know whether like a length len substring can explain spottiness. We're gonna turn it to true when we find one that works, and then yeah, and then in the end it'll just go through this condition. But in the beginning it's false. But we did already check this first substring. So like we would do like if there's actually this convenient method called collections.disjoint, where you can check if two sets are disjoint. If you didn't know about this method, it is not a big deal. Like you can just code this yourself. You would just iterate through every element of the first set and check if it's contained in the other set. I think that's probably what the disjoint method itself does. So it's just like to save space in code. We would so if they are already disjoint, that means that like we need to set work to true. So to just make this more concise, since this is just like an initial condition, we can just set works to this value, and then get rid of that condition. Okay, so now we're gonna start the process of like shifting over the hash, right? We've already set up like the hashes of like all these length lens prefixes, but now we need to be shifting them over. So we're gonna loop through. So like we're gonna be looping over the indices that we're adding. So we're gonna start this at len and then go up until m, right? Because here in this part we added all the positions from 0 up until len minus 1, right? Because like there's 0 index. So now we can be looping over the index that we're adding on. So the first thing that you would add on is len. Like if this is your initial prefix, you would add on length this distance 4 thing. I mean this index 4 thing, and then cut off this index 0 thing. So we would just so we would have to loop over all the strings again, and then just shift over their hash. So we would have to first cut off this like we would have to first cut off the first character in the current substring, which is spots of I of j minus len. Because if j is the index of the thing that we're adding on, then j minus len is the thing that we're cutting off. So is this, but then we have to multiply it by pow of pow of 0, because like basically how the hash is constructed is where like the leftmost character has value like base to the power of 0 times. But let me actually just quickly sketch out how it look like. So like I kind of drew this kind of diagram before, but pretty much like the leftmost character would have like base to the power of 0, and then the second one would have like base to the power of 1, and then so on. It would just keep building like that. So if we want to shift this over one to the like right, then we'd have to like cut off this thing and then reduce all of these things by the base to make like the new heights. Just cut off everything else, and then we would add on this like new thing to the right. So that would effectively shift everything over. The first step is to cut off this last thing, and then we have to divide by the base. So like since we can't actually divide, we multiply by the modular inverse, which is actually just the same thing as like if the base and the mod are relatively prime, we can just expo of base and to the power of mod minus 2. This is just something you have to mem, but like this is how you would divide by base. To divide something by base, you would multiply your hash by base to the power of your mod minus 2. And then also one thing is you have to add, like if this becomes a negative number, you have to add mod to it to keep it positive, because otherwise like that could cause problems with your mod being negative. So this just makes sure that it stays positive. So once we've divided by base, we have to add on this like thing to the right. So we're gonna do s hash plus equals spots of ij, because j is the index of the current thing we're adding, times power of len minus 1. Because like if this is like the exponents of the bases go from 0 to len minus 1. So the exponent of like the last thing we're adding on is len minus 1. And then in the end we have to like mod by mod just to make sure it stays less than mod. And so that pretty much finished shifting the hash for the current body string, one to the right. We can just copy and paste the same code for the plain ones. It would just be the exact same process. So we're just gonna copy that, except this have to be careful to change this. So basically at this point we finished shifting them, but we have to make sure to add them to the set, right? We have to add the new hash to the set, and same with this. But like we also have to be careful to we have to clear the set every time. because like we only want to be checking like the current range of indices with itself, right? We want to clear everything from like the previous iterations. So and at this point, if these two sets are disjoint, then that means that like we need to turn works to true. And then let's just add this condition here, not works, so we can like break out of the loop quickly if that becomes true. And then I think that is pretty much the solution. So I'm gonna copy in this input and see if this works. Okay. Oh, I think okay. I didn't do like sh of I, and the same thing has to happen here. Okay, so it gave 4, which seems to be the correct answer for that. So let's submit this to see if it works. Oh, I'm kind of using the wrong template, so I'll just like change the input files. Okay, then if we submit this, let's see if this works. So okay, so it passed all the test cases. So does anyone have questions over the solution? I think this is definitely a pretty involved problem, and it also took me longer than I expected to go through it. Oops, but it's pretty involved because like it has like binary search with hashing in it, and then like also thinking to be able to store the hashes in a set and like check if the sets are disjoint. So yeah, this is a gold problem, so it's like pretty advanced. So like it's also like completely fine if it's just like hard to follow, because it's a pretty advanced problem. But I should probably let Andrew start teaching his presentation.
All right, so let me share my screen. So my presentation is going to be a little bit easier. So I guess we can go through it a bit quicker because Victor took a bit long. But before I begin, let's go over a little bit of, I want to give a short story. So 2 nights ago, I had a really in-depth dream where the spirit of Christmas came and told me a dear friend of mine, William Yue, who's a very, very good boy, really wishes to learn some computer science soon. So this is why I'm creating this presentation on number theory, and I hope y'all enjoy. So overview over today's lecture. So first of all, we'll be going over just basics in number theory for those of y'all who aren't too familiar with math or like don't do math competitions. Second of all, we're going to talk about prime factorizations, then the Euclidean algorithm, then modular inverses, and then finally, if time permits, we'll give an example of how to use mathematical intuition. So let's begin. So what is number theory? So number theory is a very common area of math based upon studying integers. So like basically take arithmetic, go more in depth. That has widespread use in computer science, such as hashing, like last meeting's lecture, for example, how Victor explained binary exponentiation / fast modular exponentiation. That's all number theory. Then also like cryptography, like the RSA algorithm, check that out if you're interested. Proving pure math theorems. There's a lot of computer science applications onto pure math, which is kind of the opposite of how things normally work, but we can ignore that. And also quantum computing, as it's like the main facet in post-quantum cryptography. So basically, whenever you see something like mods or stuff like that, that's all going to be number theory. So let's begin with the sieve of Eratosthenes. Okay, so before I talk about this, let's give sort of an overarching question. So let's say we want to prime factorize a number. So how do we do? So first of all, we have to think of like find what numbers are primes, right? For example, like you can't really prime factorize 35 without knowing that 5 and 7 are primes. Or for example, like let's say you have 48. You have to know that 2 and 3 are primes to be able to factorize it. And then from there you can factorize it. But first you need to find what numbers are primes. And that's what the sieve is for. So the idea behind the sieve errata themes is that a number is prime if none of the smaller prime numbers divides it. And that's based on just a definition of a prime number, because the only divisors of a prime number are itself and 1. And if we iterate over the prime numbers in order, then we already marked all, since we iterate over the prime numbers in order, for example, we're iterating from like 1 through n, right? And we can check if each number is prime. That means we'll eventually mark all numbers that are divisible by at least one of the prime numbers as divisible. So if we reach a cell and it's not marked, then it's not divisible by any smaller prime number, and therefore has to be prime. And this next explanation might not make too much sense verbally, and but if you didn't understand that, just ignore what I said, and let me show you that this GIF is like a lot more instructive. I'm just going to say that. So as you can see, the first iteration, you start with 2, and because there's no numbers less than 2, 2 has to be prime. So then you just cross out all the numbers divisible by 2, because those can't be prime. And then for 3, you look at all the numbers divisible by 3 that's greater than 3. Those can't be prime. And then you see 4 is already marked off because it's divisible by 2. And then 5, you do the same thing, mark out all the numbers divisible by 5. Then 6 is already marked off. 7 hasn't been marked off, so you keep doing that, and so on and so forth. And then from there, the numbers, like when you reach a number that hasn't been marked, that means that that number is prime. So does everyone understand what I'm talking about here? As you can see, like they just mark all the multiples of 2, and then you're at 3. And then here they skip 4, it's already marked. Then 5, skip 6, you're at 7, skip 8, 9, 10, and then so on and so forth. So yeah. The thing is, if we want to find all primes less than n, we just divide by each prime less than n. So yeah, we just keep doing this. Sounds good. So this is O of n log of n time with some big constant factor. I don't know what exactly it is, but it's pretty big. And you can prove it using some asymptotic analysis, like using like prime number theorem, like Merton's theorems. It's some pretty advanced stuff that I won't get into. But you can ask me if you're interested in knowing like how to determine the time complexity of the Seyfert themes. But yeah, now that we have that, here's a quick implementation. So let's say you want to find all, this is, by the way, our code will be in C++ today, just saying. But it's basically the same as Java if you don't know C++, and I can explain. So over here, just think of this, for example, as an array of booleans with the n+1 booleans. So like, is this number prime? So obviously like 0 and 1 are not primes. That's a given. And then we can just iterate from 2 to n. So if a number is prime and the number squared is less than or equal to n, then you can just, and then you start iterating through the multiples of that number. So for example, if you start with 2, right? Because is prime 2 is automatically set to true, then this is true. And then also let's assume n is like 10 to the 5. And 2 squared is less than or equal to n. And this is important. I'll explain why we have I times I is less than or equal to n later. But if that's less than or equal to n, then we can start iterating through the multiple of 2. And then after that we iterate to 3. And we can start iterating, we can mark the multiples of 3 as all false. And then from there, we do the same. From there, we go to 4. But since 4 is prime, 4 has already been marked as false in the I equals 2 iteration, then this is going to be false. So we don't do that. Then we just go automatically to the I equals 5. And that's basically how it works. It's a really simple implementation, just 2 nested for loops. Next of all, let's talk about using the sieve to find the prime factorization of a number. So let's say we want to find the prime factorization of all numbers up to n. So you're like, okay, we need to first find all primes less than n. Well, that's wrong. We need to find all primes less than or equal to square root of n, not n. Because if there's a number less than n, not divisible by a prime in that range, then it has to be prime. So for example, let's take 35, right? So 35 is equal to 5 times 7. So in that case, you might be like, hey, but square root of 35 is rounds down to 5. So what are we going to do if we only find the primes less than 5? Well, the thing is, if there's a number less than n, which, like, for example, 7, not divisible by a prime less than or equal to square root of n, then it has to be prime. And that's, I think, a pretty basic principle a pretty basic principle, because otherwise it can't be like a multiple of anything if it's not divisible by prime in the range, which means it has to be prime. Basically, it's pretty simple. So then from here we just iterate through each prime. I forgot I can't really things, which kind of sucks. For math-based lectures, it'd be really helpful if I could write and annotate on the presentation, but that's beside the point. But anyways, from here we just iterate through each prime. So after finding all primes of the square root of n using this algorithm, we can just we find all primes up to square root of n. Then we can just check the number of powers of each prime that divide n. And if some p divides n, we can just have like p divides equal. Then this is supposed to be the other way around. N divides equal p. Sorry. Wrong button. So yeah, now you might ask, how did the square root of n thing relate to the implementation we just mentioned? Well, it's because this thing over here, because if I times I is greater than n, then all multiples of I will already be marked. Because if they're not prime, then they're going to be divisible by prime less than or equal to square root of n. And that's the same thing as what I said over here. So now let's give like the code for it. So again, this is in C++. So you have this array of primes over here, first of all, that we generated. Then we have this array of factors, basically going from smallest to largest. We'll order it from smallest to largest. And if a factor shows up multiple times, we'll just have it in the array multiple times. Actually, like array list. It's more, I guess it's more of an array list. Then basically we have for each number we look at in primes, right? For example, we have in d is in primes, right? Then if d times d is greater than n, that means d is greater than the square root of n. And in that case, we know that the remaining thing is prime, because like if it's not divisible by anything less than square root of n, then it has to be prime. Otherwise, we have this while loop, which is basically while n mod d, while n is divisible by d, then we add d to the factorization array list. Because again, n is divisible by d, so it has to be a factor. And then we just divide n by d. And we just keep doing this because it's a while loop until there's no more factors of d and n. So for example, let's take 48. Let me think of a better example. Let's take 28, right? Then for d equals 2, we don't break here. We go to this while loop. Then we divide by 2, and we add 2 at the factor. That's 4. Then n equals 14. We divide by 2 again, add 2 as another factor. Then n equals 7, and then we keep going. But now from here, when we look at, we know 7 has to be a prime. None of the prime numbers less than square root of 7 divide 7. So that's why we go to, that's when you break from this for loop. And then you move on, to this if statement, which is basically if n is greater than 1. So in the case that like n is a prime greater than n is a prime, like the final n you obtain is a prime, for example, like 7, and then you just add that factorization array list, and that's what you return. So that's the basic implementation. So this can be applied in a lot of different ways. For example, like like problems can ask a lot of different things. So for example, like create a hash map between primes and we can create a hash map between primes and powers. Like for example, like we can have like 3 associated with like 4 if we're talking about, and like 2 associated to 2 if we're talking about 324, because that's 2 squared times 3 to the 4th power. And this can be helpful for like finding like the number, sum, or like product of factors. And here's just a formula for some of them real quick. I made a typo here as well. So if we express n as a prime factorization, p of 1 to the a1 power times p2 to the a2 times dot 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 times pk to the ak, where these p of i's are just prime numbers, and then like these a of i's are the exponents, then the number of factors of n is just going to be equal to this, like the product of the exponent plus 1s. The sum of the factors is going to be the product of p1 to the a1 plus 1 minus 1 divided over, and then times like that for all primes. And the product of factors just n raised to the number of factors over 2. So I think these are 3 helpful formulas that can appear in some problems. And that's for example, like an application of prime factorization code. That like another application, like besides from just factorizing it, these are some things we can do. Now here's another. Let's see. I think I'm probably going to skip this for the sake of time because it's not too important. But just know there's a pretty quick algorithm. It's a pretty what's it called? Optimization for the sieve that can take it to O of n instead of O of n log n, which basically halves the computation time. But the real benefit comes from computing this array LP, which is basically the minimum prime factor for every number I. That's the array we form, because now we're able to find the factorization of any number from 2 to n in linear time. And the implementation basically works like this. I'll give a quick explanation actually. So yeah, over here we have, like this just like a list of the prime numbers we find. We initiate the minimum prime factor of each number as 0 because we don't know anything yet. We assume all numbers are prime, and then we'll gradually fill it. So then when we start iterating from 2 to n, if a number I is so far, if it's equal to 0, that means I is prime. Like if we iterate to I and LP of I is still 0, that means that LP of I hasn't been changed through the entire iteration, which means that I is still prime. So we just assign LP of I equals I because again, I is the smallest prime factor of I if I is prime. Then we add I to the prime list. Otherwise, if I, again, this is LP of I not, excuse me, is not equal to 0, that means that we already found the lowest common factor. We found the minimum prime factor of LP of I, which means I is composite. And by the way, the good thing about this sieve is that we only like assign each LP of I once. So for example, if we do the regular sieve code, we'll go over some numbers like twice, 3 times, 4 times. Like 30 we'll go over when we're looking at the factors of 2, factors of 3, and factors of 5. That's not going to happen when we're using this algorithm. So you might be asking now, like, how do we assign numbers to LP of I? And that's what this last part is. So in both cases, we update the values of LP for the numbers that are divisible by I. Oh, I made another typo here. However, our goal is to do so as the set of, so basically we do it as follows. Like we take the numbers x of j, which is equal to I times p of j, where p of j is all prime numbers less than or equal to LP of I. So for example, if we're looking at like a prime I, then we're just gonna set all numbers I times prime numbers less than I, and then we just set a new number LP of x of j equal to p of j for all numbers of this form, and we can do this because p of j, if p of j is less than the smallest prime factor of then the smallest prime factor of I, then of course the smallest prime factor of I times p of j is just going to be p of j. So we can just set this new value. And I think if you think about it a little bit, it's pretty clear to see how you'll set every single value exactly once. I'm not going to go through the rigorous proof of that though right now because for the sake of time. But yeah, here's the code. Again, I'm not gonna really go over it because we don't have too much time, but it's a pretty cool implementation. I think something y'all should definitely read up on. If you want a more thorough explanation, credit to cpalgorithms.com. I think they have a bit more about that. So let's go on to our next topic, which is GCD. So GCD is it's not denominator, it's divisor. Okay, so the algorithm for this is called the Euclidean algorithm to find the greatest common divisor. And if y'all don't know, the greatest common divisor of two numbers, A and B, is this number that divides both A and B. So the algorithm's pretty simple. GCD of AB is equal to A if B equals 0. Otherwise, GCD of AB is going to be GCD of B and A mod B otherwise. So here's an example. GCD of 234 and 2826. So that's going to be, obviously, like none of them are equal to 0. So it's going to be, so we can take like 234 and 2826 mod 234. So the remainder we divide 2826 by 234, and that's 18. So now it's GCD of 234 and 18. Again, none of them are 0. So we take the divides, we replace 234, the remainder of 234 divided by 18, and that's 0. So now it's just GCD of 0 and 18. And since we said over here it's equal to A of B equals 0, then that's just going to be equal to 18. So this GCD of these two numbers is just 18 using this really simple algorithm. And that can just be done within like basically a one-line code. It's actually like 2 lines, but you can definitely simplify it down to 1 line, which is using recursive implementation. Basically, if B equals 0, you return A. And if otherwise, you return B, GCD of B, A mod B. It's that easy. So let's move on after that. Again, this greatest common divisor can be used in a lot of problems, especially ones talking about simplifying fractions. I think there's one or two of those on a problem set. So this Euclidean algorithm will be pretty helpful for that. Now for modular inverses, so if you want to find the modular inverse, so first of all, a modular multiplicative inverse of an integer a is an integer x such that a times x is congruent to 1 mod x. Then x would be denoted as a to the negative 1, but it's not actually a fraction, it's just an integer. So that's like, so don't get confused between that. And by the way, the modular inverse x only exists if a and m are relatively prime. I've made another typo. So for example, 3 and 26 are relatively prime. So the modular inverse of 3 mod 26 does exist, and it's actually 9. And if you check, 3 times 9 is just congruent to 1 mod 26 because it's 27. However, if you try finding the inverse of like, let's say 4 mod 26, you can't because those two are not relatively prime. And again, if you want to find if two numbers are relatively prime, you can just use something like the Euclidean algorithm, because relatively prime means that the greatest common divisor of these two numbers is 1. So again, this is a really helpful application for that in that case. But modular inverses are pretty important for different reasons. So for example, dividing by a mod m is equivalent to multiplying by a to the negative 1 mod m, which means we don't have to deal with like modular decimals, which don't even exist. So like there's really no other way to deal with them. So for example, let's say I'm hashing, right? I'm using like some mod, and I want to divide, but I want to divide by my number by like some other number, let's say k, and we're looking at mod p. But I can't really divide it because it's a mod. So like our initial number n may not be divisible by k, but instead I'll multiply by the modular inverse of k mod p, so k to the negative 1. So how do we find that modular inverse? We have 2 methods that we go through. First of all, it's called extended Euclidean. So for this one, I'm not going to actually explain the full algorithm for the sake of time, but I'll just go over the gist of it. So we're trying to find the inverse of a mod m, where we know a and m. So consider the equation ax plus my equals 1. If we find an integer solution for x and y, then we found the modular inverse of a. And you might ask, like, why? Well, we can just take this equation mod m. So mod m, this thing my just goes away. So then it just becomes ax is congruent to 1 mod m. And that's exactly what we want to find. We want to find x such that ax is congruent to 1 mod m. That's the definition of x being a modular inverse. So that's literally all we have to do. We find a solution to this and we're done. And we can use the extended Euclidean algorithm, which to solve this Diophantine equation. That's the type of equation this is. And we can use it again, since we know a and m, we just have to find some x and y that are integers. And excuse me, and we can just find that by again using this extended Euclidean algorithm. So you can check out Wikipedia, ask me, or go on like cpalgorithms.com. But here's the code of it basically. And this is pretty helpful for a variety of uses, not just finding modular inverses, but this is just an example. Now, this second way is probably something that y'all already know. So I think it'll be a bit more clear. So Euler's totient theorem says that if A and M are relatively prime, then A raised to the phi of n is congruent to 1 mod m. And by the way, phi of n is just this. So like n times 1 minus 1 over p of n times dot dot times 1 over 1 minus p of k. So again, you have to prime factorize n to figure out phi of n. But yeah, then a to the phi of n is congruent to 1. And this means that, and what this also means that is a to the phi of n minus 1 would be congruent to a to the minus 1 because it's the modular, which means it would be the modular inverse, which means we just have to find a to the phi of n minus 1. And we already know that this thing, like based on the definition of this function, is going to be like an actual integer because it's a positive power of a. So that's something we can just do here. And moreover, if p is a prime, which is a special case of Euler's totient theorem, then we know that a to the p minus 1 is congruent to 1 mod p. In that case, we would just have a to the p minus 2 is congruent to a to the negative 1 mod p. So a to the p minus 2 would be the modular inverse of a. And again, and that would be an integer, of course, because p minus 2 would be non-negative. And now to find that, we would just use, to find like the power of a, like it could be like a really big power of a, but we can still find that really quickly using fast modular exponentiation, like basically what Victor explained last week. And we can use that to compute these powers, such as in this code. I'm not going to explain it because I think Victor already explained that during the hashing lecture last week. So yeah, now that's the second way of finding modular inverses. So again, this is widely applicable, especially when you're working with a lot of mods like in hashing. So now next of all, I was going to go over this example, but I think we're a little bit short on time. So I'm probably just going to skip this because it's not too relevant to any of the previous topics. It was just an example of mathematical intuition with Fibonacci numbers. But the essence of it is just playing with patterns and trying to find some patterns. But I will not explain that today, I guess. So yeah, thanks for coming, everyone. And here's some problems for y'all to work on. This hackering problem set. You can just click this. I'll copy paste this link in the chat. Where is the chat? Okay, I'll copy paste it here. Yeah, this will be the problem set for today. So over here, there's going to be 4 problems. If you look over here, it only said there's 1 problem. That's on here because the first 3 problems will be on code forces. This won't be officially graded or scored or anything. It's just the first 3 problems are on code forces, and this 4th problem, which is honestly probably the easiest problem, is something you'll submit over here right on HackerRank. So yeah, again, that's going to be the lecture for today. So thank y'all for coming, and I hope y'all have fun. Does anyone have any questions?